In order to simplify expressions that have a complex number in the denominator, or an imaginary number in the denominator, like the two examples that we see here and here, we have to take advantage of what are called complex conjugates. And so this sort of thing is used for simplifying expressions where there's a square root in the denominator. And we really have that in this circumstance. Even though we don't see the square root, we have to remember that I is equal to the square root of -1. And a rule in math is that you're not allowed to have a square root in the denominator for something to be considered in simplified form. And so what we can do is we can take advantage of these complex conjugates to help clear out the I from the denominator. And so a complex conjugate is just a pair of expressions where the real and imaginary parts are identical. So it's the same number that's real, it's the same number that's in front of the I for the imaginary part. The only difference is one is positive, one is negative for the imaginary parts. And if we multiply a pair of conjugates, complex conjugates, we will always end up with a real answer. And this comes back to the idea of a difference of squares. If I have x minus a times x plus a, my result is going to be the multiplication of the firsts, which will give me x squared, and then just the multiplication of the lasts, which will be minus a squared. And those outer and inner terms of the full FOIL will cancel each other out, because I'll get a positive xa and a negative xa, so those will be opposites. And so if I multiply two expressions that fall in this pattern, something plus and something minus, but the same thing in both sets of parentheses, then those middle terms disappear, or in the case of conjugates, those imaginary pieces disappear, and we're going to end up being left with just a couple of real numbers. So let's see how we can use complex conjugates to help clean up these expressions so we no longer have an I in the denominator. So let me clear out these arrows here, then we can get to work. So what we're going to do is we're going to multiply both the top and the bottom by the conjugate of the denominator. So in this case, if I have 1 minus 3i, the conjugate is going to be 1 plus 3i. And so I have to do the same thing to both the top and the bottom of the expression, because otherwise I would be changing the value of the expression. I'm just trying to change how it looks. I'm not trying to change what its value is. And so in both the top and the bottom, we're going to have to do our full FOIL multiplication of the two binomials that we have, the two complex numbers that we have. But on the bottom, it's going to always work out, if we use this conjugate pair, it's always going to work out so that the imaginary parts will disappear and we'll be left with a real number. So there will no longer be an I in the denominator. So I'm going to go ahead and do that multiplication off to the side here just so that we have a little bit more space. So I have 1 minus 3i times 1 plus 3i. So when I FOIL that, I get 1 times 1, which is 1. I multiply my outer, so 1 times 3i is 3i. I multiply the inner pieces, which is negative 3i times 1, so I get negative 3i. And then finally I get negative 3i times positive 3i, so minus 9i squared. And so what we see is when we go to gather the like terms in the middle, those three i's, one is positive, one is negative, they cancel each other out. And then the only I that I have left is an I squared, which hopefully we remember is, remember, I squared equals -1. If I square I square root -1, so the square and the square root cancel each other out, so we just get -1. So that means I now have 1 minus 9 times -1, or 1 negative 9 times -1 is positive 9, so 1 plus 9, where I end up with 10 in the denominator when I'm all done. Now for the numerator, I have to do a full FOIL, and it's okay if I end up with an imaginary number when I'm all done. It's no problem to have an imaginary in the numerator, it's just the denominator that we have to concern ourselves with. So again, I'm going to go off to the side here to do this multiplication. So I've got 6 minus 7i times 1 plus 3i. And so if we go with our full FOIL, I get 6 times 1 is 6. My outer is 6 times 3i, so I get 18i. My inner is negative 7i times 1, so just negative 7i. And then my last is going to be negative 7i times positive 3i, so negative 21i squared. And so now I need to do the same sort of thing, but unlike in the denominator, my i's in the middle there don't cancel each other out. So I've got the 6 still, plus now 18i minus 7i is 11i, but on the back end here I do have this negative 21 times I squared, which gets replaced with negative 1. And so then to close things out here, 6 and then plus 11i, and then I have plus 21. So to finish off, I'm going to gather my like terms. So 21 plus 6 is 27. So I've got 27 plus 11i in my numerator. So this is our simplified expression. It's equal to what we had in the original problem. It looks very different, but it no longer has an I in the denominator, which is the rule breaker that we have to try to work around. For the second example, we're going to do the same thing. We're going to multiply the top and bottom by the conjugate pair of the bottom. So 4 minus I, I'm going to multiply it by 4 plus I. So I keep everything the same, but I just change the positive negative sign of the expression. So I have to do the same thing to the top and the bottom. So on the bottom, we're going to FOIL this out. So I'm going to get 4 times 4 is 16. And then I know those outer and inner terms are going to cancel each other out. So I'm just going to skip them. So I've multiplied the firsts, and then I'm just going to multiply the lasts. Negative I times positive I gives me negative I squared. And then on the top, I've got to do my full FOIL. I can't skip anything because I'm not going to get the same canceling out of those middle terms like I did on the bottom. So if I FOIL, 5 times 4 is 20. My outer term is 5 times I, so I get plus 5i. My inner term is negative 2i times 4, so I get negative 8i. And then finally my lasts are negative 2i times I, so negative 2i squared. So I've got some simplifying to do in both the top and the bottom. So I've got in the top 20, then I've got 5i minus 8i, so that gives me negative 3i. And then I'm going to change that I squared to a negative 1, so I've got negative 2 or minus 2 times negative 1. On the bottom, all I have to do is just change that I squared to negative 1, so it's going to be 16 instead of minus I squared, it's going to be 16 minus negative 1. So up in the top, I've got 20 minus 3i, and then negative 2 times negative 1 is positive 2. On the bottom, I've got 16 minus negative 1, so that's going to become 16 plus 1. And so then to close things out, we just gather our like terms in both the top and the bottom. 20 plus 2 gives me 22, minus 3i, and then all over 16 plus 1 is 17. So again, we haven't changed the value of our expression, we've just changed how it looks. We've dealt with the issue of having an I in the denominator, which is a rule breaker, by multiplying the top and bottom by that conjugate pair of the denominator to eliminate the I and get a real number in the bottom.